In the second part of section 16.7, we'll continue surface integrals, this time for vector fields. In surface integrals of vector fields, we'll take the normal component of vector field. So the normal vector must be well defined. It must be at least continuous. That is related with oriented surfaces. Let's see the definition. S is a vector representation R. Then the uninormal vector n is defined as R sub u cross R sub v divided by its length. The surface S is called an oriented surface if the uninormal vector varies continuously over the surface. A counterexample is a Möbius strip, which is made with from a strip. Is one side, one end is turned 180 degrees and attached, so that if you start with a normal vector, for example, at this point, okay, then if you move along this surface, then you turn around, and now the normal vector from the point will be pointing inside that side, right side, so that the normal vector is not continuous, so it's not an oriented surface. Okay. But for this one, and it's moving continuously, and so that it is an oriented surface. You may choose n here, that direction, or inside another one. So that's the reason you see here chosen. Okay. For closed surfaces, the positive orientation is the one outward. For example, if this one is whole sphere, then the outer normal vector is positive orientation. Okay. Okay. And when you try to see if it is oriented surface, then you may think this one. Surface S is called an orientable if it has two separate sides. For this one, it has one and another one inside, but for that one, it's now that's out, but go in and again turn around, it becomes out. So there's no two sides. Sides are connected to each other. Okay, so it is not orientable. We have a historic view for surface integrals of vector fields. When the vector field is the velocity of fluid, then the flux, that is the fluid passing through the surface, and once fluid is moving along the tangential direction, then one side or the other side, there's no fluid change. So that once you try to compute the flux, then you may consider the normal component, so that only the normal component contributes to the flux. And because the flux is defined as the quantity of fluid flowing through the surface per unit time. So that when we try to compute the surface integral of vector field, we are taking only the normal component. That is definition. Yeah, the vector field is continuous vector field and defined on an oriented surface with a unit normal vector. The surface integral of the vector field over S is defined in this way. the integral is called the flux of S across S, so that we try to measure the quantity of fluid passing across the surface. Once you are considering line integral, then we say along the line. But now for surface, we say across the surface, because physically only across the surface has some meaning. For line integral, along the line has meaning. So we distinguish in this way. Now, that is definition. So here we announced that for surface integral, we try to compute the quantity in normal direction only. That is definition. Now, by using identities, we can deal with this right side effectively. N is given in this way, and ds, along with a scaling factor, and dA, and this integral can be transferred to the regional, flat regional integral. So we can deal with the integral much more easily. Okay. Now, combine them. We have here the formula, and that is the definition. We are using identities for n and ds, here and here. And we can cancel these two terms, and we recheck this one. We have to express the vector field as a function of u and v, and along with this normal component dot product, we can get this scalar function, and we can get integral. Okay. This is quite similar to line integrals of vector fields. And again, here for flux, we say across the surface. For line integral, we say along the curve. Okay. Now, f dot dr, okay, that is definition. We are considering only a tangential direction. And now, along with known identities, we have that and simplify. So we can use this one for calculation. And again, same way, this is for evaluation. We are using this formula for evaluation. But sometimes this definition is useful in some examples. Okay, we'll see here. Okay, find the flux of the vector field across the upwind helicoid. And helicoid is parameterized like that. And u is from 0 to 2. And that is now, okay, u, that is length, so that direction. And v is here rotation, and in z direction up, so that pi, half rotation and coming up. Okay, that is helicoid. And for that one, here if we try to get also u and also v, then we have that. Right? So the flux over there, so we'll use that. You can compute that one. Okay, let's try to compute in detail. Okay, now, okay, R sub u. From here, u derivative, then there's cosine v and sine v, and last form must be 0. And how about also v derivative minus u sine v, from second one u cosine v, u cosine v, and that must be 1. Now r sub u cross r sub v is determinant of metric the metric is this one. So from here, for I, now that, okay, AD minus BC, so there must be sine V, right? And for J, this one minus that one, minus cosine V. And for K, okay, AD minus BC. So U cosine squared V minus U sine squared V, so that there must be U. Sorry. Okay. Now for FR, we have to express the vector field as a function of U and V. X is U cosine V, Y is U sine V. And that is 1. Now, if you try to get f of r dot product with r sub u, r sub v, then, okay, this product will be u sine v cosine v. There is a minus u sine v cosine v. It's cancel out, and we'll have only u. Okay. So the flux, the given integral, is same as now integral over d, and we have only u and dA, right? Okay. Now that is a rectangle. U is from 0 to 2, and v is from 0 to pi. 0 to pi, and 0 to 2, and u du, and the, okay, u is from 0 to 2, and v is 0 to pi. Okay. So it is v independent. So we have a pi from v integral, and for u integral, we have half u squared, and from 0 to 2. So we have here 2, so that 2 pi. Hooray, we have the right answer. Okay. Now we'll see this problem. It's using spherical coordinates, so that it takes a little bit of time. So I pre-calculated the results. Okay. Find the flux of F. The vector field is z, y, x across the unit sphere. Now, so that we have to find the first vector representation of the surface. Because it's a sphere, we may try to use spherical coordinates. This time, rho is 1 because the radius 1. So that is exactly the spherical coordinates with rho replaced by 1. So we have this representation. Phi is from 0 to pi, and theta is 0 to 2 pi. This horizontal rotation, this is from North Pole, angle from North Pole. Then FR, ZYX, ZYX, that's exactly this one. And if you compute that cross product, then you will get that one. It's a little bit time consuming. So I put here the result. And once you make a dot product of these two vectors, then you have that. So the flux, start with this notation. Now this is computing formula. And on this spherical rectangle, we have that result. Okay. We have two terms. You may consider now separately. First, look at that one. That is a theta, and okay, phi and theta separable. For if we focus on only this one, then you can get theta integration. Theta is from 0 to pi. Phi is from 0 to pi. And theta is from 0 to 2 pi. For this part, halfly positive, halfly negative. So the integration for that one will be 0. So that this whole term will disappear. The value must be 0. So we have only this one. Now again, this is separable. So that theta integration and phi integration. And for this one, okay, we may use formula. What is that? This one is half and 1 minus cosine 2 theta, right? So that again, this one has no contribution. So half is used along with 2 pi. We have pi. For this portion, we'll have 4 over 3. Okay. For evaluation of this one, we did earlier. So you may remember that. Okay. How can we do that? That is, okay, we'll write down here, sine cubed theta. That is sine theta and sine squared theta. By using the well-known formula, we change this one. That's 1 minus cosine squared theta. Then that is same as now sine theta and minus sine theta cosine squared theta. What is this antiderivative? Okay, that is, okay, that's minus cosine theta, right? And for this one, okay, plus 1/3 cosine cubed theta, right? Okay, that is the antiderivative, and we are evaluating from 0 to pi. So from this one, you'll get 1. From this one, you'll get 1/3, so that you have 4 over 3, I believe. Okay. Yeah, anyway, you evaluate from 0 to 1, then you will have 4 over 3. Okay? Okay. For this example, you can get the value quite easily. In fact, in the last section, we'll deal with the surface integral for closed surface. This unit sphere is closed surface. For that one, it is basically the volumetric inside integral of divergence of that one. X derivative, Y derivative, Z derivative summation, which is 1. So that is the volume of a sphere, which is now 4 over 3 pi r cubed. R is 1, so that must be the solution. Okay? So we can get the integral, surface integral, when surface is closed, and we can get it quite easily by using a formula which is called divergence theorem. Okay? We'll deal with that in the last section. Okay. Now we considered the major part of the surface integral of vector fields. Here we consider a special case. Surface defined by z equals g of xy, then a vector representation can be made in this way. R of xy equals xy and g of xy. Its normal vector is found in this way. Of course, you can get it from that the level surface. So try to get gradient, then you can reach that one. It's easy to memorize. So that the surface integral of the vector field PQR in formula, the evaluation formula, we have that. And if we put PQR and that one, then you can reach at this one. This one is a little bit confusing, so that don't try to memorize this one. Try to use here, because you can get this quantity, that quantity. So that try to make practically the dot product, then it's easier. If you try to use this, then this negation is involved, so that you can easily make a mistake. Okay, evaluate this flux where F is y, x, z, and S is the boundary of the solid region enclosed by the paraboloid and plane z equals 0. Okay. Now, so that is closed surface. Let's try to visualize it. X direction, Y direction, Z direction. Okay, the paraboloid is 1 minus x squared minus y squared. So that we have that one. And then z equals 0. So we have this one. Okay. The solid region E and S is the boundary, so that now it's close to the surface. And let's say this side that's made z equal 1 minus x squared minus y squared, and side is S1, let's say bottom is S2. Okay. Then for S1, okay, let's begin with S1. The parameterization is naturally, we are using this one. Of course, that one is from D to S1, and here D must be this bottom, right? So S2 is basically the D, but anyway, we'll write down explicitly there's x squared plus y squared is bounded by 1, right? That is there. Okay. Now, FR, what is FR? And now, R sub x cross R sub y, we'll try to get that one here. Okay, that is yxz. So there's y. xy are independent variable, and z is 1 minus x squared minus y squared, and dot product. And that must be, okay, that is g of xy minus g sub x. G sub x is 2x, and a minus 2x, so along with a minus, that is 2x. G sub y is minus 2y, minus of that is 2y, and 1. Right? Okay, so we have now that one is the same as 2xy, again 2xy, so that is 1 minus x squared minus y squared plus 4xy. Right? Okay, so the surface integral over S1 is the same as now double integral over D of this quantity, 1 minus x squared minus y squared plus 4xy, and dA. A is a polar region, a disk of radius 1, so that angle is from 0 to 2 pi, whole circulation, r is from 0 to 1, this one is 1 minus r squared, and for that one, plus 4, there's r cosine theta, r sine theta. So there's r squared cosine theta, sine theta, and we have to have a scaling factor r, dr, d theta. Right? Okay. Now, for that one, okay, now we have to get integral. So we may consider separately along with R multiplication. But when we do, then there is theta component. But for that one, this one is same as, okay, half sine 2 theta. Okay, so that theta is moving from 0 to 2 pi, then 2 theta will move from 0 to 4 pi, so that it's halfly positive, halfly negative. So it is 0. Or you may think it's antiderivative. Then this one is same as half sine squared theta, right? If you try to make derivative, then 2 will go out, and sine theta, cosine theta. So it's antiderivative. It's evaluated from 0 to 2 pi, when 0 is 0, when 2 pi again 0. So that no contribution from this one. So we may ignore this part. So already made the part is now along with this r minus r cubed there. Okay, so theta independent. So there's 2 pi immediately. And from 0 to 1, now r minus r cubed dr. Okay, from this one, there's 2 pi, and we'll have from this one half, from this one 1/4, so that there's 1/4, so that pi over 2 is the answer for the first part, S1. Now we'll go to S2. Okay, S2. Okay, this one. Now that one, of course, you can do similarly along with some parameterization, but that one, we have to consider this one as 2, and now f dot n ds, right? Now for bottom, n is 0, 0, minus 1. Only we have that minus 1. So we can deal with this one quite easily. And what is f? Y, x, z. So this dot product, f dot n is, okay, y, x, z, and here 0, 0, minus 1. So that is same as minus z. But on bottom, z value is 0. So that must be 0. So we have no contribution from the bottom. So that must be 0. So final answer must be the summation of these two, which is pi over 2. Right? Okay. For your homework problems, I collected this formula here. So try to look at this formula table and try to solve the problem using the formulas. Okay? Thank you.